Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to look at how we solve logarithmic equations. So far we've talked about the bases of logarithms, we've talked about the properties of logarithms, we've talked about how to convert from log notation into exponential notation. Now we're going to use all of that knowledge to help us solve logarithmic equations. So basically a logarithmic equation is an equation that contains an unknown in the quantity part of the logarithm. So an example of that we've kind of already done. We learned that we could find this quantity. And the way that I suggested you do it is you go from log notation to exponential notation, and then that isolates your quantity, or the q. So that's what I'm going to do here. My base is 3, my exponent is 4, and that's what q is equal to. Now we just find 3 to the 4th, and we're done. So that's the simplest type of log equation you can solve. Let's look at some that are more challenging. In my second example, I have a coefficient in front of my log term, and we can't go into exponential notation when that's there. You can't simply plug in the way we did in the last example. You have to deal with this coefficient. Two options. You can either use your properties of logs and make this whole expression on this side log of m squared, base 4. But because we're trying to solve for m, I'm going to avoid getting powers of my unknown. So the other option, and what I would prefer to do, is I'm going to divide both sides by this coefficient. So negative 3 divided by 2 on this side. When I divide by 2 on this side, I'll simply have the log of m base 4. Now that you have it, the log of something equals whatever, now we can go into exponential. But when you have a coefficient there, you can't do it. So now when we go into exponential form, our base is 4 to the negative 3 halves will equal m. We could calculate this on our calculator. I'm going to do it without a calculator because it's something that we can actually calculate. Negative exponent means 1 over the base, so 1/4 to the power of positive 3 halves. So if you don't understand what I did there, go back and check the video on exponents, in particular fractional and negative exponents. Now this will be equal to square root of 4 cubed. Again, that's in that video on fractional exponents. Square root of 4 is 2 cubed. So m will equal 1/8, or if you did it on your calculator, you're going to get 0.125. Either answer, they're equivalent, so that's fine. The next example is one that's an actual real life kind of application. It's in chemistry, and it's the formula for pH. And pH is defined as negative log of the concentration of hydrogen ions. So if, for example, you knew the pH and you were asked to solve for the concentration, that's in the quantity, so it's a log equation. So we would put in 3.2 for pH. And just think of this just like I did the q or an x or whatever variable you want. Don't get, bogged down by the looks of that variable. Again, we have a coefficient here. We don't want to have that coefficient. We cannot go into log notation if there's any coefficient here other than 1. So I'm going to multiply both sides by negative 1. So we're going to get negative 3.2 equals the log of the concentration of hydrogen ions. Now I can go into exponential notation. There's no base stated, so we know that means base 10. My exponent is negative 3.2. When you're dealing with powers of 10, if you have integers, you can leave them. If that had been just a negative 3, I could leave it as negative 3, 10 to the negative 3. I don't need to evaluate that. But if my exponent is a decimal value, I need to calculate that. So I'm going to use my anti-log function, or my 10 to the x key on my calculator, and I will get 0.00063. That would be the concentration if the pH of a solution is 3.2. Let's take a look at another few examples. Okay, the next example is going to look very complicated, but I wanted to use another application. This one is one in electronics. So it looks scary, I understand, but just stick with me here and I'll just show you, I'll take you through this step by step. So we have an equation here, the natural log of I divided by I sub 0 is equal to negative r times t divided by L. So we don't need to know what all of these things mean, but I represents current at time t. I sub 0 represents the current at time 0 seconds, so the initial current. R represents the resistance, T represents time, and L represents inductance. So we could be given a formula like that, and I could be asked to solve for any one of those variables. I'm going to do an example where we're going to solve for a variable inside this quantity to show you how you need to go from log notation to exponential notation the way that we did with the previous examples. So let's plug in what we do know. We don't know I. It says find I if I sub 0 is 1.5 amperes. And don't worry about these units. That's just the units that are used for those types of measurements, but you don't get bogged down by those. Resistance is 10 ohms. Time is 0.25 seconds. And inductance is 2 henries. So it's a little bit better than it was because now we have numbers, but let's just simplify this expression here. So I'm going to have natural log of I divided by 1.5 equals, when I multiply 10 times 0.25, I get 2.5, divided by 2 is 1.25, and it's negative. So now it's looking much easier. When you get these formulas and you can plug a lot of the values in, do as much simplifying as you can before you proceed. There's nothing more I can do here. I can't touch this I. And one thing I want to caution you about, you also cannot touch the 1.5. Some people want to multiply both sides by 1.5. It's part of a natural log quantity. You can't touch it until you get it out of that quantity position. So what we're going to do is go to exponential form. So we're working with natural log. We know our base is e. This is our exponent. And that's equal to our quantity. So remember, I'm just going from that's all I did. I had the log of a quantity equals an exponent. So I take my base, which is e in this case, raise it to that exponent, and that will equal the quantity. So, that's a very important ability to have when you're solving log equations. Now I want to solve for I. I'm going to multiply both sides by 1.5. So 1.5 times e to the negative 1.25 will equal I. And when I evaluate that, I always try to leave my evaluation till the end rather than calculate this and then do the multiplication, because if you're doing calculations along the way and you're rounding off, you're introducing error into your answer. So if you can just keep the expression without actually calculating it until the very end, then your answer is going to be much more exact. So when we plug this into the calculator, find e to the negative 1.25, you're going to use your e to the x key, your natural antilog key. You're going to find that, multiply by 1.5, and we should get an answer of 0.43. I know that this is current, so I know that the unit will be amperes, but unless you're into doing electronics questions, you might not be expected to worry about the units at this point. But I just wanted to show you a few examples of real life situations where you will be dealing with logs, or you may be dealing with logs. And I just want to step you through that so that you weren't too intimidated. Let's look at a couple of examples where we have more than one log term in our equation. Okay, in this question we have more than one log term in our equation. But when you have more than one log term, this is not like multiplication. You cannot multiply through by log base 2. It doesn't work that way. This is not log base 2 times 4. It's the log of 4. So we can't simply divide through by that. What we need to do is, when you have more than one log term, is you want to combine your log terms, and you want to do that using your properties. So we learned how to combine these two terms. It will be multiplication, 4 times x, and I can do that because I have the same base. Now that I have the log terms combined, I just have the log of something equals something else. That's in log notation. I can express that in exponential notation. So my base is 2, my exponent is 3, that's equal to 4x. Now I can evaluate. 2 cubed is 8, so x is equal to 2. All right, in this example, we have all of our terms are log terms. So it's a little bit different of an approach when we have this situation. What I would do first is deal with this coefficient, because I can't really do anything with that term while it has a coefficient. So I'm going to use my property of logs. Before, when I dealt with that coefficient, I divided. But if I divide by 3, I'm going to end up with a 1/3 coefficient there and a 1/3 coefficient there. So that's going to make it worse. So this time I am going to use my properties of logs. And I don't mind using it when it's a number and I raise it to a power. That's not a big deal. So this will be equal to the log of 2 cubed. Now I've got a couple of options here. I could combine these two log terms by using my second property of logs, or because my unknown is in here, maybe I want to move that over. So I could express this as log of t equals the log of 4. I'm going to add that term to both sides plus the log of 2 cubed. Actually, let's write that as 8. Then I can combine these two log terms. So it's up to you which method is easiest or preferred. To combine these, now I'm going to use my first property of logs that says this will be equal to the log of 4 times 8. Now this is a different situation because I have a log term of, a log of t equals the log of 32. I can't go into exponential notation. In this case, if you encounter an equation like that, if you have the log of, let's say, m equals the log of n, and the base is the same, then you can say that m has to equal n. The only way that the log of two quantities can equal each other is if the quantities are equal to each other. So in this case, and I'm not dividing by log, don't think that I'm dividing by log. I'm just saying that if the log of one quantity equals the log of another quantity, those two quantities are equal. So therefore, t is equal to 32. So that might be a log equation that you encounter where all of your terms are log terms. So either they're not all log terms and you simplify to one log term equals a number and then you go into exponential notation, or if they're all log terms, you get log terms together on one side, log terms together on the other side, and then you end up with this scenario. So try some of these on your own and go back and watch the examples if you need. And the next video that we're going to cover is exponential equations, but we need logarithms to solve those. So practice these first and we'll see you on the next video.